There we go. All right, we're going to continue today with the nanocellulose nanocomposites. We're starting again with that wound dressing hydrogel. We're looking at the different aspects it has of it. And one of the things about hydrogels is that they typically are swollen with water, but it doesn't necessarily have to be water. It can be, you know, a blood serum. It can be, if you're doing some other process like purification of metals, it can actually be an acidic slurry or a basic slurry. You just have to make sure your gel is compatible with it. Okay, so in this case here, when we have those field wound dressing with the hydrogels, you know, this is actually probably loaded with a saline solution. So it's keeping the pH of a pH buffered saline solution. So it's keeping the moisture there. It's not just pure water, because then it'd be sucking salts out of the body. And so it'll probably be one of those saline solutions there. Now, another way to kind of use these cellulose nanocrystals here, and first of all, what purpose do the nanocrystals serve? Rheological modifier, and when it gels, it gives it a little more structure than if it didn't have them there. Remember, they're active, they have a slight aspect ratio to it, but they're not too big, and they have hydrophilic surfaces. They have hydrophilic surfaces, so they themselves have water absorbed to the surface of them, keeping these things and fairly well hydrated, but also giving them mechanical strength. Okay. So would we want to use these nanocrystals if we wanted to do flame resistance or electrical conductivity? No, they're not going to help there at all. But here they're helping it compatibilize with water and biological fluids, and therefore this is a great use for it. And again, it's biodegradable, and so when you just, you know, get rid of it, it is gone. Okay. So another thing that you can use these nanocrystals is to, again, keeping things not natural, but keeping things to be hypoallergenic. Okay, let's say if you want to have a sensor and it's stuck to your skin, you have to make sure the adhesive doesn't cause you irritation. You got to make sure whatever your gel is doesn't cause irritation. It doesn't have some kind of skin contact issue. So you don't want to use polyurethanes, because a lot of people are sensitive to that. You don't want to use latex, because people are sensitive to that. But here we're using paper, and I've never heard of a paper allergy, or paper cuts, but not a paper allergy. So that's where one of these, having these things as a component in your hydrogel actually helps you. Okay, so in this example here, they were actually trying to make some cool sensors, biosensors. And so what they wanted to see was, can we detect, using a flexible biosensor that's glued to the skin, heart rate? And so they're looking for that bump, changing the electrical conductivity. So if you look at here, this is the ratio of the resistance that you have without a stress and with a stress here. And this dark line right here is in the relaxation. They're seeing that they see some signals that are associated with the relaxation. And during exercise, they seem to be sensing something. Now, it could be heart rate, but it also could be clouded by the muscle changing the surface. So depending on the exercise condition, you can see they have a little bit more work to kind of isolate the difference between a Z-axis strain versus a Y-axis strain. So if you can actually do the Z-axis strain only and eliminate the Y-axis strain, then you'll know it's just the bump from the pulse rate. Okay, so they have a lot of different things that they can use for these. In this particular one, now we're going off to a hydrogel that you're trying to absorb pollutants. Okay, so you can imagine you might start with it dry and then dump it into something that's polluted. And during its process of taking up water, filling that hydrogel with a fluid, it's going to incorporate things to it. And the pores have to be the right size to incorporate a dye or a heavy metal. And so in the first one here, we have just PVA, which is polyvinyl alcohol. And so the carbon and then the cellulose nanocrystals, and HEMA is, it's a difunctional, anyway, But what they do is they turn it into beads. And they photopolymerize it, and then they freeze dry thaw. Okay. Okay, so now you have these dry beads that already still have their free volume because you froze dry them. Freeze dry them, froze dry them. And then you can throw them into contaminated water, and they're going to suck up dyes with high efficiency as they suck up the liquid. So in the next one here, it's again hemo-based. It's a diacrylate or something. Methacrylic acid, something methacrylic acid. Used it. Anyway, so then they have it with acrylic acid, and then what they do is a radical polymerization. And this was able to do a crystal violet. Crystal violet is actually a horrible material to work with. One crystal turns your entire lab purple.
Hydroxyethyl methacrylate.
It's hydroxyethyl methacrylate. I knew it was a water soluble, water soluble acrylic
Or white column.
Okay, thank you. So with that, you have the HEMA actually has a hydroxyl group on it, right? Okay. And that's part of the hydrophobic part. That's what helps it swell the water. Well, and then by cross-linking the system, that keeps the gel structure together. And having the cellulose in there gives you the physical properties here. And again, these are typically done in beads or powder form, and you're throwing precipitated material, contaminated material, and then they swell up and they get filtered out. And that's how you remove them from the system. Again, we can do with some other ones, and we're okay with these, the Biosensors. You end up doing what they call, they usually use butyraldehyde as a cross-linking agent. It's really toxic, so I don't recommend it. But the chemical cross-linking, the aldehyde groups react with any of the amines in the system to create an amine, and that gives us a chemical cross-link here. And they were able to isolate methylene blue. And when they did about the same thing with grafting and did a freeze dry, they were also. But the cool thing is the last two also, well, the last one was also able to pick up bidentate heavy metals and silver. Okay, we don't typically think of silver as a major contaminant, but things like mercury and nickel are definitely, and I believe that's copper. So in high concentrations, copper is also. But notice they're bidentate, which means once they get in there, they're going to be bonded to one hydroxy over here, and you can't get it out. It's going to be irreversibly bound into the system. And that's the benefit of having these hydrogels, because you have so many hydroxyl groups on there, and you also have tons of hydroxyl groups on the surface of your nanocellulose, crystalline nanocellulose. Okay, so what does that kind of look like right here? So this is kind of the structure here. And what they're looking at is that you have hydrogen bonding. So this is an actual chain of a polysaccharide. That's an actual chain of a polysaccharide. But there's hydrogen bonding in between the two. And as you fill that stuff with, so this is where the crystallization of these cellulose nanocrystals comes from. It's an intramolecular. There's intramolecular and intermolecular hydrogen bonding, allowing us to form those big crystals. And in this particular one, they also did cellulose nanofibers and oxidized cellulose nanofibers. So when you look for these, we see on the top two, those are the nanocrystals that we have, and they are as made and then oxidized. And so that's going to change the surface reactivity. So we should see a change in the physical properties of it. And then we have the cellulose nanofibers and then oxidized cellulose. So now what we're doing is we're taking those hydroxyls and converting them to carboxylic acid. So now we're changing the nature of the binding that they can do. Okay. And when you do that, they were able to, let's see, they were using it for, oh, that was just reviewing, saying that those are two different options. So you can actually change the buffer system that works better with the oxidized versus the as received. Okay, so let's see, where are we going to go with this? So now, most of the time we're looking at the cellulose here, but that's not the only thing you can extract from naturally occurring fibrous materials. Okay, so we can get the amylose or the amylopectin right here. This is what we call hyaluronic acid. Okay, it's an acid because it's been partially oxidized. You got this carboxylic acids, amine functionalities, amide functionalities here. And this is usually made with the glucosamine, which has a nitrogen on it, replaces one of the oxygens with nitrogen, gives it a different characteristic, it gives it a different isoelectric point, because this is more basic than these. Then we can also do chitin. Chitin is the exoskeleton on a lot of beetles and stuff like that. You notice it's a little bit different here because we use two of the glucosamines, and we've had them functionalized here, so they don't hydrogen bond as well, but they are, that makes them actually a little more soluble. So you can actually use the chitin and the chitosane for other things. Okay. So then there's also the hemicellulose. Okay, hemicellulose is not as linear as regular cellulose here. It has an extra group here that this is a 5-membered ring here, a fructose with this binding group on it. This is a unusual one. Usually they're not this conjugated, but what we have here is just a standard starch chain, but it has these side groups on it and changing its properties. Okay, so and you get the different things from different places. Okay, so well, all of these are found in natural fibers. You tend to have more hemicellulose on the outside and more of the nice, perfect cellulose stuff wrapped around the other cellulose derivatives on it. So you have to actually get rid of that, which is not the crystalline structure that we have. Okay, so lignin is also another one of those things that really is a complication, because if you try to make alcohol out of carbohydrates like this and try to break them down like that, lignin actually inhibits, is not useful in the actual production of alcohol from braided fibers and fabrics. And so what they saw was that they could actually process these materials, and in this case, they are making silk Fibron scaffolds and they're using electrospinning. Okay, you guys know what electrospinning is? Okay, so they take solutions of this, and notice that the size of the fibers change with the concentration. Okay, so if you think about it here in electrospinning, you have a high voltage, you're shooting out of this cone, and so the viscosity is going to be a major component on how fast it's going to accelerate out of the cone. So if it's a lower viscosity, it's going to accelerate faster than if it's a higher viscosity. Okay, so that means it's a higher draw length, which means it's a narrower fiber. So we see the progression here, just 1% difference between all these. These are all the same bar size. We see an increasing, I mean, there's right here, like a really important viscosity parameter here. We see we get various types of things from a soluble silk fibron. The silk fibrons that are made are actually synthetically made by bacteria.
So what is electrospinning concentrations? What is exactly that?
Okay, what this means is it's 7% of the fibron in solution. So so you have 100 grams of the solution, 7 grams of the solution polymer. Okay, or 8 grams or 9 grams. So then they figured out that when they processed these things and added to them some lignin-derived nanoparticles, not nanocrystalline lignin, by the way, because it wasn't a full crystalline, but they showed that they could have gram-positive and gram-negative bioactivity significantly lower silver concentrations than conventional agents. So what they did was they took the great thing about silver being a great antibacterial agent, and instead of having to have a large mass of the silver, they put this activated surface on here and put a lower dose of silver in it that had an even better activity. And so it could, with a wide range of antibacterial activity, because gram-positive and gram-negative are two different types of bacteria, and usually only one surface works with one surface works with the other. It's unusual to see them with both. although that's new, now the new multifunctional materials, we're seeing a lot more of them covering both systems. And actually silver does cover both systems. It's one of the weird things. Okay. So another way to do it would be to use a chitosan alginate nonwoven. Again, this is through an electrospinning process where you alternate or actually you commingle those two materials, and by having them electrospin, they're not woven. And so you end up with a lot of free volume, a lot of disorder. Okay, so you have a lot of place to actually suck materials in and store them. So these were used to make biocompatible cyto, meaning cell compatible, and did not activate an immunogenic response and inhibited E. coli. So just the thing itself, no silver, no anything, just these fine nanofibers that were created by electrospinning were able to accomplish that task by making it inhospitable for E. coli, but not having a problem with affecting platelets, it didn't affect clotting, it didn't affect, and it didn't cause a white blood cell response. It went the wound. Okay, so why? Have these, starch derivatives. They're made from long chain sugars, and we are incorporating these long chain sugars every time we. So
This is like a certain topical cap.
Then this is for a topical cap.
So the question is, why is it not eliciting a response?
Yeah.
Because the skin is made of pulp. It's pretty similar.
Well, but you have an open wound too. So,
But when you blend together, the structure of whatever we want to blend together, and does not allow security.
yeah, and that's for things coming on. But why doesn't the body reject it?
I would guess that it looks like skin, but
We ingest all these different types of starches already. Our body is used to having this in our system. Not necessarily on the skin, but it does not produce an immune response to the polysaccharides and chitosan. It does not produce an allergic response unless you have like, yeah, and those are very rare. The true allergies to those, where you have some kind of bowel issue right here. So you are naturally trained to not have a biological response. So using a biological system, a highly purified biological system, so it's not pure, but using a biological system to be inherently non-rejective. So it's actually a very clever idea. Okay. So the results of this review were that the environmentally friendly biopolymers are increasing at a rate, and they actually did a thing where they looked at patents too. The number of patents was going up, the number of publications were going up. And there's a lot of potential here due to the advantageous properties of biocompatibility, biodegradability, low immunogenicity properties of these polymers. Okay, because we're used to being exposed to them all the time, every day, multiple times a day sometimes. Significant progress has been successful tissue engineering, implants, healing, and dressing and delivery systems. Again, it goes to that compatibility and lack of rejection. Lack of rejection really drives some of these properties, and why, I bet we would have some rejection and stuff for things like clay. And actually, clay is generally regarded as safe, but some of the other nanoparticles, cadmium selenides, probably not something you want in your body in there. And anyway, but what they did say was we still have to worry about production methods. Okay, so there's really good stuff out there. There's some production out there, but it's not to the point where every Band-Aid you're going to see is made out of this kind of nanocomposite. And part of it is that, okay, let's say you're extracting your nanocellulose crystals out of pine. Okay, total mass of nanocellulose crystals in your pine you can extract 3%. So you got to chew up 97% of your tree just to get through it. So there needs to be a better way to grow them or something that makes it better. And these biosorbent stents, which are things that you can actually put inside cell walls that hold things apart and then hold things together, and will slowly dissolve because your body can dissolve them without any response. And then you still need to do it within humans. They've started it on cells. I think there was a couple studies with pigs, which is the closest analog to us as far as biology goes. So that's a good sign. Okay. All right. So that is the end of part 1. Let me pull up part 2. Okay. So in this one, we're going to start with a bunch of different places that they're being used by different things and their sources. Okay. So wood pulp is one place to get nanocellulose and crystals. Cellulose nanocrystals and nanofibers. But when we look at how to get them, sometimes it's really hard. In the case of this, they're using a nanocrystalline cellulose from cotton. Actually, cotton is a pretty darn good source of it, but again, it's also a commodity source for other things too, so it's a competitive market. And then they compatibilize it with this polyvinyl alcohol and polyvinyl acetate. Again, the polymer has hydroxyls on it. The nanocrystals have hydroxyls on it. It's a good compatibilization. And they saw improved dynamic, tensile, and Young's modulus, of course. And they had a slight, significant temperature difference when they added the nanocrystals. A glass transition temperature rose significantly by adding the nanocrystals. Why? And that's the glass transition of the polymer rose significantly.
When they ask there's less polymer.
No, I mean, no.
So can you ask a question again? Sorry.
Okay. The glass transition temperature rose significantly with the addition of cotton, nanocrystals.
Because it acts as like a crystallization site. So.
Partially true. And it's hydrogen bonding to something that is not flexible. So you got a flexible chain here, it's bonding to the surface of the nanocrystal, you got a flexible chain here, bonding to the surface of the nanocrystal. It's acting as a crossing. And therefore your transition from going from your glassy state to your rubbery state, your higher free volume state, gets pushed higher and higher because you have to overcome more interactions. You don't have to overcome just the polymer reactions, you also have to undergo the polymer nanocrystal interactions. And the chances are you're going to have more than one polymer on your nanocrystal. So you have to overcome more than one interaction. So it significantly shifts it to higher.
Does the heat transfer the 2 different materials?
No, not the heat transfer. You have to, those bonds that are usually hydrogen bonds, you still have to apply enough heat for them to break apart from their substrate, or at least move from this to this one and get enough chain mobility so that they can migrate. As they can get enough chain mobility to migrate or have the chains move, that's going from the glassy state to the more rubbery state. Okay, so then if we get it from flax, which is probably a better thing to do, and mix it with nitrile rubber, we again get a tensile strength increase, which we expected, and a higher thermal degradation temperature. Nitrile rubber, let's see, nitrile rubber is just, yeah, it's an insulator, and the carbon the cellulose nanocrystals are high thermal conductivity, higher than the nitrile, but not very high. And the TG shifted 7 degrees with 20 parts per 100. That's almost 20% loading. 18% loading. So why would it have a higher thermal degradation?
When the crystal rise.
Yeah.
Transfer.
I think it's because what's happening is that you have, like 18%, 8% there, And the nanocrystals decompose later than nitrile rubber, so your purchase gets shifted out because your nanocrystals haven't started to decompose. But they didn't give a reason for why it was higher. And again, it was only like 5 or 10 degrees, so it could easily be lost in this curve. But this is reproducible and significant. Okay, so then if we got the nanocrystals out of palm oil instead, I'm sorry, oil palm, the actual palm fronds from oil palm, and mix it with polypropylene and rubber here, we saw an interface surface tension and thermal stability. What is interphase surface tension? So polypropylene is a very non-polar polymer, right? And the natural natural rubber is probably going to be a lot more hydrophilic. So what we're seeing here is that the polypropylene doesn't want to interpenetrate with it and mix perfectly. So they make phase domains. But if you have your material at those phase domains, there's some parts of the rubber that can bond to it, and the polypropylene is probably just crystallizing on the surface there, giving it a better interface. And that better interface means you change the thermal stability of it. The individual phases melt at different temperatures, therefore hopefully higher temperatures than you have. And it was more homogeneous than with no fillers. Again, what you're doing is those polymers don't want to mix. But what you're doing is letting them mix to smaller bodies by having the nanocrystals be able to support both sides. And you can get smaller and smaller phases, making it seem more homogeneous. Okay, so I don't know how they extracted it out of pineapple. I assume it might be just the tops, but not necessarily the fruit. I didn't figure that part out. And with polyvinyl alcohol, it's a great substrate for the system here, used to develop green hydrogels, pH sensitive and magnetic sensitive hydrogels. So they're swelling them and looking for the properties, improve thermal stability and swelling ability. Okay, because it's acting as that crosslinks, it gives you a more stable swollen material, significant enhancement of loading and entrapment efficiency. That's, I believe, a dye that they're using to use for water purification. And then sisal leaf, that's another one of those crops that is really kind of not really known well in the United States, but it does have a lot of significant fiber. Again, tensile properties as we expect for something like this, especially if partially aligned.
Is the swelling able to find something preferable?
Well, if you're harvesting the top part, or with the plants, because there's a whole other part of the plant that, and this is just the fruit on it. If you have to recycle those into something instead of burning them, then there is a waste stream for pineapple. Assuming you're not looking at the fruit, I'm assuming you're looking at the palm. It's a bromeliad, and so it actually grows with fronds, not fronds. Leaflets coming up, and it has a big leaflet ball in the bottom.
That's where I thought they grew.
No, pineapples grow in the ground. Yeah, they're about this big, and then that's the fruit that comes up. Kind of like an artichoke. An artichoke is part of the sunflower.
So, how many of these fibers have like commercializable?
That's a really good question. I do have a slide a little bit on that, about commercialization toward the end here, and I will share that. But yeah, there are definitely some sources that are easier than others. Things that are non-food sources, like if it's a pineapple waste source, they're going to do something with it anyway, so it'll be free. There was a team, MSEEC team that did rice husks, and they were able to isolate nanosilica out of rice husks. And so, and that was a waste product. So the guys were like, here, you can have 20 tons. No, not 20 tons. Maybe they're at the 20-ton mark now. I don't know. So when we go to a craft pulp, so this is basically stuff like pine, fir, polyvinyl alcohol, had good strength, increased the thermal degradation in TG, better crystallinity because of the bonds between the sugars and the nano and the polyvinyl alcohol. So this is kind of, I want to show you that the diversity of where you can get these nanocrystals is amazing. In epoxies, it improves tensile strength and has good adhesion, which is interesting, and it has better dynamic mechanical properties. So imagine you're getting your better tan delta. Epoxies are pretty brittle, so having any kind of flexible filler, that's probably helpful. Okay, and I don't even know what the gassy pulp is, but they saw the same things there. And not sure why they say aluminum nitride, or they're using that as a cross-linking agent. Aluminum can bond 3 times to anions, and so they might be using it as a cross-linking agent, so there's not technically a polymer here. Made it highly suitable for green electronics, and made the have improved thermal conductivity. Again, probably because of the cross-linking between the two. And then banana, I again assume from the tree, not the actual fruit. True, but most of the time when you have a pineapple tree, there's a huge. I believe technically they're grasses, but yeah. I never took a biology. I haven't taken biology since high school. All I know plants get some gardening. So. Okay, so just a little bit gives a increased water uptake in film, which is really important for epoxies. Epoxies aren't really fit for uptake in water. Good, significant with just 2 or 3. Act as a catalytic curing agent. I bet they found that out by accident. Stirring. So they probably had to back their catalyst off a little bit. If you think about it, there's a lot of surface energy on these things, a lot of hydroxyls. Normally, you would use an amine curing agent for an epoxy system because it's more nucleophilic. There's lots of hydroxyls here, and I'm sure that it's chemically bonded to the epoxy matrix as well.
So that's causing crossing.
In this case, yeah, because the hydroxyls on the surface of the nanocrystals can react with the epoxy, they do react slower than with the amine, but they can. So I think it is actually chemically bound to the system, but also kicking off the reaction. Okay, how many more of these do I have? Oh my God.
How many references do they have?
This one had, I want to say like around 300 references.
I think the Tunicate one was the one that was nanocrystals and it was the mechanically adapted.
And so this one is, wood, cedar, bamboo, all showing increased properties in the chemical properties. So it doesn't matter where you get them. If you process them correctly, for some substrates, like you have to use a silane treatment or something to get into some substrates. But it's really diverse at the ways you can use them and the way you can find them. So I think that, once you find a feedstock that's cheap and an easy way to purify it, it becomes a little more commercially viable. Okay. Maize starch, which means even corn, that's probably a bad source. You make alcohol out of that. So, just for carbs, okay. The mate de coco, which is the husk of the coconut, or the actually I was thinking it's the cocoa bean is the husk of the cocoa bean. Bamboo, coffee silver skin. Okay, so in a coffee bean, you actually have a fruit around them. When you pull that off, there's a skin layer in between there. And then the bean itself is green. You have to dry that. Then they turn into a tan. And then you roast them and then they get really dramatic. You're actually thermally decomposing some of the stuff in the bean to make it taste good. Caffeine's there in the raw. So the silver skin is this barrier that's in between the fruit and the actual. But again, well, that seems like a lot of the source. Trying to isolate that from the rest of the stuff. I'm assuming
It's probably the waste. waste.
Yeah,
all mixed
it's a waste
together.
stream. They've just had a graduate student.
Or chemical extraction.
Yeah, so. Yeah, it's a lot lighter than the husk. They could have just done air, low air and just have it collect up. So, I don't know where they got their microcrystalline cellulose here. But they're seeing the same properties with the nanocrystals. Let's see, nanocrystalline cellulose, KNF. All right. So here's where we're going to talk about commercial viability. Okay. So if we look at the possibility of what comes from what, there's a composition in hardwood has almost 50% of cellulose, but has a lot of hemicellulose, lignin, and then pectin and waxes. These are things that are water insoluble, so extractable that way. Okay. So this is from this review that I'm looking at commercial applications of nanocellulose. So we're going to talk commercial applications. Softwoods about the same, But some things like jute has a very high and the lignins lower and low fatty extractables. Okay. So that might be a good one. Jute is actually a very easy to do. Wheat straw is a waste product. Corn straw is a waste product. Oh, sugar cane, that is the fibrous material that might have to squeeze the juice out. That's a waste product. That's a waste product. That's a waste product.
What is jute?
Jute is used to make rope in string. It's a really fibrous material. It's for jute backs. Yeah, it's woven and burlap is woven jute.
Oh, okay.
Pineapple leaf, so it is the leaf right here, still pretty high. A lot of it waxy extractables though. So the hardwood and softwood have a waste stream, but most of the time that goes in paper. Okay, and out of sawmills you get the powder and the paper. Some of these other ones that are waste streams of the production, they're going to burn it or something anyway. So that's a good place. But I mean, if you're going to start a business, I think jute might be a good place to start, especially because you have less of the lignin, which is one of the harder things to get rid of. So that would make a place to do your business. Well, around here, though, we have a lot of cotton and real hemp.
Well, you think the industrial.
I think I have a slide on hemp, and it wasn't very okay. It wasn't very high, but I think it has other medicinal purposes.
No fun.
Yeah, we're not in Colorado.
Yeah.
Okay, yeah. So again, this is kind of the way that we looked at before. We had the nanofibrils that you do by mechanical process because you don't want to break the in-between joints of the nanocrystals. You have the nanocrystals that are by hydrolysis, you're taking away these non-things. But then I said there's a third type that we hadn't talked about that. And it's the hairy cellulose nanocrystals. And so it's chemically treated, but they use a weaker acid or a basic version such that it leaves long tendrils hanging off the end. Yeah. And so I think that might lead to better compatibility with some things. And so you might have better tie-in with the polymer matrix actually improving physical properties versus the nanocrystal part. So when we're looking at our materials that we're going to be incorporating, we have to think about what we're doing, right? What are we doing? Are we just going to increase our thermal conductivity? Well, then we need to pick a filler that will have a good persistence length. Probably want to co-mingle that with a spherical one so you can have connections between those long persistent materials. And then you want to make sure you decide whether or not you need electrical conductivity. You don't want electrical conductivity. I did a project for Philips once. They were trying to improve their irons. They wanted a material that was rubbery that could transfer heat better than the rubber that they were using now because it was actually too expensive. Using it to find these things up. So we came up with a process around it, but we had a requirement. Had to have no electrical conductivity or nothing above the rubber. So that really shrank our number of materials that we could use down and missed their price point. So it's not commercially available, sorry. But it was fun, let me tell you.
Like $1 per.
$1 per unit,
Oh,
$1 per unit. So I can't tell you what it was, but it was, $1 was too much. We were $1 over what they wanted. At full production rate. Huh?
is it really too much? Like $1?
Well, when you sell 5 million of them a year,
$5 million. That's a lot of costs. I'm not.
anyway, because they were competing with another thing, so they had to keep the same price point. Anyway, that's one of those things we got to compare and contrast. Okay, so in this case, the nano or fibrillate one can be made from the nanofibers or microcellulose fibers. Can come from a lot of different sources here, and they can be extracted mechanically with decent lengths and diameters between 5 and 16 nanometers. But look at it, several micrometers long. That's a big aspect ratio. You can modify that by the type of mechanical processing you do. If you're doing a physical ball milling, you actually get longer fibers than if you do high shear homogenization. Because in high shear homogenization, you have them whipping around and they start breaking apart. So your process also controls final product, not only your starting material. And in this case here, if we want the nanocrystalline cellulose, some of the best ones are cotton and hemp and flax. Right? But they can also be synthetic grown by algae and bacteria. In fact, that makes it easier to isolate because most of the bacteria and algae, well, the bacteria at least have fleshy bodies that are easy to get rid of. And the crystals that don't have are already just crystals, they're not fibrils. They're only made as crystals. So, you know, just kind of do some cell lysation and filter them off. So that's actually probably a good way to do it industrially. Just have a huge bacteria farm that just pumps out nanocrystals. Okay, and then, but you can get these whiskers or rods, and the diameter is usually about the same as the nanofibrils, maybe a little less. But the length is about 1/4 to 1/10 of. Okay, so the diameter is the same, but they're about 1/10 the size. But remember, these are not flexible anymore. The fibrils have those flexible joints. So you're going to have a rigid place and a flex joint, rigid place, flex joint. You eliminate that when you go to here. Even though they're shorter, there's no flexible space. So the entire thing itself is doing all of the work. Okay. And then, if we want to go just to the bacterial cellulose right here, you can use low molecular weight sugars other than sucrose and glucose, which is what we have in most of our other starches. You can use a bunch of different of the less beneficial sugars, things that we can't process, things that cause humans biological upset, like sugar alcohols and stuff like that. You can use those things. The bacteria don't care. They're going to make those crystals that way. But I mean, the size varies a bit, but they can be made depending on how the bacteria grows. They'll be a little bit larger in diameter, and you get really weird sugars and sugar alcohols, things that are not things we can use. So that's actually a nice waste stream as well. But again, if you can do it from the bacteria, that's a great way to do it. But any of the waste products from wood or cotton is also a decent source. Okay. And I have. Okay. All right. Now, the other cool thing is carbon nanotubes are hard to functionalize, right? We have to heat them in acid and do a little bit on the functionalization. Graphene, if we over functionalize it, it turns to graphene oxide, and we aromatize it. In the case of our nanocrystals or nanofibrils here, they are inherently built in to have alcohol groups all over the outside. As soon as you isolate them, they are functionalized. And so, depending on what you want to do, you can do a wide variety of things like compatibilizing it with ethers, compatibilizing with aromatics. In fact, we'd want something like this or something like this if you wanted to mix graphene in with it. Why? High stacking, exactly. So you want, and this one's nice and flat too. So this is going to help compatibilize graphene into your system. Get one with the carboxylic acid here, and you can go with one of those functionalized nanotubes. Get an amine functionalized nanotube, and you can go with that. That one over there has a negative charge on it now. It's made into the acetate salt. So you have a negative charge. Now you can go layer by layer, just with the same thing. Silicones, get it into long chain polymers like polyethylene. That would actually be most compatible with polybutadiene, because it has a double bond in there. That double bond in that top can be used to vulcanize it with polybutadiene in there. So another compatibilization. Again, nice pegs in the water system. I thought I saw one with fluorine on it somewhere. Bromine. Thought I saw one with fluorine on there, so you have like a fluorogroup on there to maybe get some Teflon materials as well. Of course, that's not biodegradable. Okay, so how can we actually use these? Okay, so the processing, which we haven't actually done that much about, right here is we can do what they call hand lamination. And so in hand lamination, it's analogous to making fiberglass. You lay down a glass mat, you rub on the resin. Lay down a glass mat, you rub on that. In this case, you're putting down paper fibers, dry fibers inside a mold, and you're rolling the resin on it like a cure. Okay, so the resin has to be low enough viscosity to infuse into your system and have a decent enough cure so that you can reuse the mold. But another way to do it is a little bit faster. And oh gosh, I forgot the acronym again. Not reaction, resin something. Resin transfer. Resin transfer molding. I knew I was going to forget. So in the case of resin transfer molding, this is how they make bumpers. They're polyurethane bumpers. You actually have two very fast reacting materials. A lot of times it's polyurethanes or polycyclobutadiene. They can catalyze it very fast. And what you do is you close the mold, and with some kind of substrate support, you inject them both in. The mold, the reaction's done in like 30 seconds to 2 minutes. Pops the mold open, put another mold in again. I actually got to see one of these at Dow once. It was really cool. They might make small boats like that, but most of the boats that I've seen are they're fiberglass, and they're made by the way of them.
Probably do spray, right?
Chopped fiber spray. Yeah, definitely. So yeah, another one is where you actually have a long, literally a couple miles of glass fiber, a gun, and so you're spraying your two components of your resin out, and then as it's doing that, it's chopping the fibers as you spray it. So you don't have a huge pile of chopped fibers, so you don't have to worry about viscosity problems. It's actually spewing the dry fibers on there all through the same net. You just go however many layers is on there. Okay, so let's see. Then, depending on your polymer system, you can actually just do compression molding. If it has thermoplastic enough, you can do that with putting in whatever your system is and having it just close like a standard. When it's cooled enough, you're ready to cool it and then eject your molded sample. So again, you have to be careful about the thermal window on these because we do see a slight increase, but not 500 degrees C thing. So we have to worry about that. And of course, injection molding, which is again a high production process that we can probably use for doing that, especially for small biocompatible medical devices, a lot of medical devices, injection molding method. And if you really want to go crazy and do fibers, there's this extrusion method, which means the fibers themselves are dry when you start. Okay, So imagine you have 10 things of fibers here that you get pulled through the bath. And then at the other end, they're weaving the fibers together. Imagine a woven case on something. Then as it goes through the heated dye, it presses it down and then gets it all. So it's a cured tube. Right? So you get additional strength by having the weaving. There used to be a machine in England where they were making composite cases for fuel tanks and helium tanks and everything like that. And they called it the Dragon. The reason they called it the Dragon was because to get their adhesive, to get their matrix to stick to their fibers, they had to do a flame, a low oxygen flame plasma treatment immediately before. So literally there was flame shooting out of this thing as right before it goes into the bath with epoxy, and then it's being wound on a multi-axis manifold.
The reason for that was like flat surface.
It oxidized the surface just enough to really mechanically and chemically bound. But it's something like polypropylene. Put a surface treatment on polypropylene, 24 hours it's gone. But something about the way they did it that was like, we don't have to pre-treat our fibers anymore. We don't have to care how long they've been sitting there. We're just going to pre-treat the fiber as we use it. So that would also probably not work for this. It'd probably catch on fire, actually.
Yeah.
So then we talked about this one, LBL. LBL is a really good one because of the surface charge. Like I said, you can modify it to have a positive surface charge or a negative surface charge. You get a mean functionality, quaternary ammonium. You can get a carboxylic acid salt, and you can do layer by layer or spin here. And this one is actually the more traditional one where you dip into one and then dip into a lens. It can be a continuous process. If you're making smaller things, the spin one's actually kind of cool because you go thin layer and then spin off everything else. And only what's stuck to it electrostatically stays on there. Do another one, spin off everything else. Another one, spin off everything else. Again, this will only work with flat substrates, so if you're making like electronics or something like that. But then there is a spray process, and that's how we used to do that here, where you spray, rinse, spray, rinse, spray, rinse. And that's usually done with air guns or something like that. And we've seen this one done, not for nanocellulose and any of the things I saw, but we did see nanocomposite membranes made this way using carbon nanotubes and a mixture of graphene palettes and carbon nanotubes, where you get a nice suspension and you suck it down into a cake. You center and or dry that cake and then infuse it. And in this case here, they're going to have they would have this dry cake that you would have to process, either infuse it with the resin or do something else to it, because this is just the nanomaterial as its compact structure. Well, what might be an advantage of having such a compact structure like that? Think about how much of your material is the nano. Could you get an 80% loading liquid as it's flowing? If you tried to load it up, if you wanted 80% nanomaterial, you couldn't stir that, right? The radiological properties would be horrible. But if you have a very low viscosity matrix, you can infuse that already structured piece. And we're assuming it's already structured because as it's going down, they're going to kind of compact and get a fairly compact structure. So imagine you wanted something that was 90% nanocellulose. And then you would just infuse it with some low molecular weight polyurethane that would zip up. So that'd be one adventure. And then, of course, the one pot directed assembly sort of kind of works, except, of course, whenever we see evaporation like this, we usually get compaction. So, but it does work for sol gel. I mean, it does work for hydrogels, because once you get your compact thing, you have no more water in there. Now you grind that up now, when you put it in water, it'll swell to 10 or 20 times its volume. So this works for something like hydrogen, especially if you're going to turn it into pellets or something. Okay, so of these methods, we have some commercially viable methods. Compression molding, infrastructure's there. Hand lamination, infrastructure's there. Resin transfer molding, infrastructure's there. All of these. So all of these, you know, all you need to do is change your parameters slightly. And if it's going to be used in a medical, you'll have to do everything will have to be washed down every shift and everything like that. But again, those production facilities exist. LBL, I have still yet to see a commercially viable LBL process at this point. It might be, yeah, you have a huge waste stream in rinse waters, stuff like that. This, I mean, that's very limited. This is going to be for laboratory only, just to prove your point. This, again, laboratory only. At the beginning of this talk, when we were talking about production methods, they said bulk polymerization versus solution polymerization. And bulk polymerization is actually more economically viable because then you don't have a solid to get rid of. Solution processing can give you greater variability. And it takes a little bit more. So I think none of these yet are going to be a really good commercial version of these.
And what about the economics?
The economics?
The cheap or affordable?
Again, it's going to be feedstock and process and benefit. What's the value add? If you have a cheap feedstock, it's easy to process, and you have a customer willing to pay. That's where you're going to have it. I wonder if you could put nanocrystals in concrete, because they do that, because a lot of hydroxyls, it should bind to the matrix really well. And then it would dehydrate differently. It would slow down dehydration because it itself would. 3D printable concrete. Cool. I didn't find a paper on that, but I just thought about it. Okay, so then there's the last two, which are almost, well, I guess it's technically. Electrospinning, they actually have a lot of things where they do commercial electrospinning. There's a production line in Russia, there used to be, where they actually solved a lot of the problems that they didn't use a single spinneret. They use spinnerets of 80 nozzles in them, and they alternate them. So they make 8-foot wide sheets that would make, you know, thick mats in a matter of hours. The only problem with electrospinning is if you want to do it commercially, you have to spin out of water. So this nanocrystalline stuff with the water-based is a great opportunity for that. So imagine making those wound mats, right? You want to do electrospun fibers, you want to do it with water because you don't want the explosion risk. There's a lot of solvent evaporating off as you do this. So just being able to get rid of the water as you do it makes these mats really commercially viable. Because again, you don't need much production. You just need to have a way to keep those needles clog free. And the best way to do that is just pre-filter. Then there's just a polymer spinning, wet spinning. This is how Kevlar fibers are made. They use sulfuric acid and they coagulate in water. So that's like they still do that. They haven't done anything different in 60 years. But then they pull it up and wind up. Freeze drying is becoming actually commercially viable. A lot of people who do aerogels do freeze drying. In fact, there's a company in Seguin that does commercial freeze drying mostly for the pharmaceutical industry. But they have a freeze dryer the size of one of those shipping containers. And they have all the pumps and everything. They can literally do, 1 ton at one shot. It's a batch process, but the infrastructure is there.
They just chop it up.
Well, no, it's in individual containers.
Oh.
So when they do a huge production run, like most pharmaceutical stuff, if it's not stable wet, what they do is they ship it dry in vials, and then at the medical facility they put in a saline or saline substitute, get it stored up, and so that way it leads to the long-term stability of the material you have. Think about it, that Pfizer thing has to be kept at negative 100 or something. It's better now. It got a better stabilizer. But it used to come in, I mean, there was a, yeah, the COVID task force literally was searching everywhere for anybody who had a -80 freezer. And so they came to the university and said, how many -80 freezers do you have? We have this many -80 freezers. Okay. Good. You're going to be on our list. We might need you. We might need you. So, okay. So then some other ways to do it, especially if you're going to do microelectronics, is the mass-based system here. Especially if you're making really tiny structures. Photolithography is again really commonly used, and photopure polymers are really easy to use. As long as you're not using a material that inhibits the photopolymerization, you can do this pattern system. And then, of course, once you have your pattern structure, you can build up other structures on it or peel it off or bend it to something else. Inkjet printing is coming in its own. I mean, there's a lot of things that are being inkjet printed now. I actually have also done 3D printed explosives. So 3D printing is also. It's probably going to make, again, you have to remove it from the substrate, so you have to be careful about cast it on. And then these are kind of cool where they use, it's called disruptive interference in their UV mask. So you do this destructive interference, and so some of the light is coming to it, and some of it isn't. Some of it cancels each other out. So you can actually have a pattern that looks kind of like a square with these 3 round things, with little things on each corner, and it'll actually make a perfect square because of destructive interference. And so then you can get to the tiny little microshells. And notice these are 2-sided, so there's a hydrophilic side and hydrophilic side, and you can get to have them do self-assembly. Okay, so again, the commercial applications that are possible, construction, like I said, nanocellulose. If you've got a cheap source and it does the property you want, then you get electronic sensors, specifically biological sensors, wearable sensors, biodegradable sensors. Okay, and note, so I did some research on profit margin, expected profit margin for a patent in a bunch of different fields. So in construction, okay, your profit margin, if you're bringing a new product to market, is probably going to be 2%, maybe 4%. Really. Okay. You go into aerospace, your profit margin can jump between 20 and 40%. I'm sorry, 20 and 30%.
It's a relatively small industry.
Oh, because who's paying? Government.
That money's fake.
So what about the optical properties of these cells?
Good question. I did not find any. I should have.
If they are like light transmittance or something like that, they can be used in the glowing structures.
Yeah, they're small enough not to fract light. But then how would that change?
It depends upon if they have the diffuse transmission or the direct transmission.
But again, they're smaller than the wavelength of light. Well, I guess even the large crystals are like, yeah. Ooh, if you align them, you'd have birefringence. I didn't find anything on the optical properties. I wasn't in any of the so hydrogels, of course, paints and coatings, modifying paints to make them tougher using a biodegradable material. That's a great idea. Paper and pulp industry, turns out just like 2% addition of the fibrils increases paper strength. Okay. So it helps bind the bigger fibrils together with smaller fibrils. Implants, especially biological systems, ultrafiltration, because you can get word structures, you can get ultrafiltration. Packaging for food products, and then composites. Seems to be a
biofilm. That
biofilm.
I don't mean.
They don't mean like waste product biofilm. They make a film that is biocompatible. Packaging is biocompatible. Or biocomposable, decomposable. And so, and what would they use them for? All right, so in the composites and plastics, extended shelf life. Why? Extended shelf life. What extends shelf life?
Maintaining those bonds.
Okay, but as a barrier, what does the barrier have to do to extend velocity? Good or bad? Bad. Yeah. You want to keep oxygen. That's the #1 thing that causes food spoilage. Either oxygen or one of their gaseous not decomposition, but causes them to become sweeter, curing. I'm not curing that. Not fermenting. So, for example, if you have a pear that's not done, you put it in a bag with an apple. The apple produces ethylene, and then it ripens. If you keep the thing that keeps something out from ripening, or keeps the thing that helps it ripen in, you can control your shelf life. And then dimensional stability. Obviously, we have nice crossing area. Packaging, because of intelligent packaging, and the fact that these have, apparently they're fairly see-through because they also have transparent packaging. Ultraviolet screening. Interesting. Normally, when you think about things in ultraviolet stream, you think about things that absorb in the UV. The sugars don't really absorb it that much, so it must be the crystals themselves. Antimicrobial, because they do that naturally. Drug release, scaffolds, implants. Barrier properties, life extension, down gauging of films. Why would you want to down gauge films? Yeah, you use less material. It's more biodegradable because it's thinner. It's hopefully less cost. Oxygen scavenger. Okay. Time temperature indicator. Because you can do a superposition of its degradation properties, you can see what the temperature over time is done by looking at the decomposition. Freshness indicator, gas leak detector. So if you have a gas permeable one, a selective gas permeable one, you can use it as a sensor. Sensors for food monitoring that are built into your packaging. They,
Color change.
yeah, from green all the way to red. Don't eat this. Single processing and a self-healing mechanism in aerogels. Because you have those dynamic hydrogen bonds, you can self-heal. You can actually take, I've seen an example where you took a hydrogel, they ground it up, there was a bunch of little stuff, and then they set it back in and heat it up to 40 degrees with one mass with 90% of its properties. With just one cycle.
They do it by themselves, or there is a technique phenomenon with that?
It's basically a thermal rearrangement of the hydrogen bonding.
They need to bridge.
Remember the nanocrystals have a lot more bonding to them. So if they break them apart, and they're going to be part of the glue that holds them together. Okay, so now let's get to who's actually doing what right now. Okay, in Norway, they're producing only 350 kilograms a day. That's probably not a commercially viable thing, but it's only their pilot plant. So that's not too bad. So the next one is also in Sweden, but it's pre-commercialization. So it's basically somebody trying to get money from VC. And so we have a bunch of different people who are trying to commit to it. Paper company, which makes sense because that's a vertical.
They have written the scale of the process. All of them are like the
Pilot or pre-pilot, right? But the fact that the fact that anybody's in pre-pilot stage or pilot stage means what?
Well, that was 2012. I was going to say this is
sorry. So hopefully, I see what you're saying. So hopefully there's some, I should have looked that up. Sorry. I didn't notice it's 2012. I thought that was 2012. 300 kilos a day, 100 kilos a day, 15 kilos a day. Look how they're making them here, wait, enzymatic. Enzymatic pre-treated. Nanocrystalline cellulose from root vegetables, i.e. carrots. So again, I think anything that comes up with a process that uses a food stock is probably not going to be economically viable. But the enzymatic process on feedstocks that are non-human consumable are probably pretty good. And here's just a few of the patents as they were accelerating through 2018. These are just some of the ones that they're using here. But what we saw was that in approximately 2000, it was 2000 when they started, there were maybe 3 or 4 patents on nanocellulose of any kind. And by 2018, I think there was like 500 of them. And those are all world patents. So that has definitely accelerated 100 times in about 18 years.
Yeah. What's the European?
All of these were European. This is a European review.
World patent.
World patent.
I've honestly never heard
Oh, you never heard of world patent? Okay. So, okay, when you patent something in the United States, if you want to patent it outside the United States, you actually have to do a PCT, which is it's the patent something treaty. And so if you want to patent outside of the United States, you have to file a PCT and not just a standard patent. Once you get approval for the PCT, then you apply to all the different countries who want that patent to force. Okay, and so if you there's a concept called the world patent where if you 25 countries or more, it's qualified as a world patent. You can also do just Europe and do an EP, which is a European patent.
how many European countries.
No, you only need one. Yeah, you can do an EP. And the strategy that my international patent lawyer does is he always sends it to Germany first. Because if you pass Germany, everybody else will rubber stamp. But every country has a different filing fee. So some of them are really high, like Japan, I think it's $20,000 to file. And then the process takes a while, and you have to have translators and that. Some countries are pretty cheap. Some countries are, hey, you have that patent, I'll just rubber stamp it.
None of them take the US as a rubber stamp? Wow.
Which is why you file a PCT, so you have the opportunity within a year of your patent to be granted here to file for your international patents. And you can do just, if you want to do it, it can cost like $250,000. So you got to really know.
But your proprietary information is only good for those countries.
True, but also nobody can import your proprietary material into those countries. So, but let's say you file an injunction against a company in China for and therefore that stops their trade adding to those countries.
So that's why you.
Then they just sell it. But that's the strategy. That's the strategy. That's how you do it. And I think that's my last slide. So what I hope that you see from this is, we can start with all these, really hard materials, but that's not the only way to do it. And that's, just, not burning down a house is not the nanomaterials. And so in fact, burning down the house will be the next one, which is explosives. Sorry.
I have like a random thing what I was saying earlier. That cocoa one source is actually not the husk. It comes from the fermented milk, and it's actually bacterial cellulose.
Oh,
So
really?
it's just another bacterial cellulose.
Okay, but it comes from the milk of the cocoa.
Fermented, which is a traditional Filipino dessert.
Wow.
Yeah.
I did not.
Cool. So yeah, so it's actually a bacterial source.
Oh, wow. Well, yeah, those are good. I think bacterial sources are great.
Yeah.
Um,
Yeah.
all right, I'm gonna go ahead and stop recording.